All right. Well, I had hoped that we were going to get to this at the end of class last time, but we didn't. So now, I did have one promise. Do you remember what the promise was? You were going to like this.
Yep.
Remember that?
I do remember that.
Okay, so here is what we're going to do today. We are going to learn about assembly language. Now, let me lay this on you. So far, all of the programs that you've written for this PEP8 computer have been in which language?
Java. No.
No.
Machine.
Machine language. And at what level of abstraction? 3, which is called the what level?
Instruction set architecture.
Instruction set architecture. That's the ISA level. Okay, so you have been writing programs in machine language. Now, how would you like it if every program that you ever had to write in your whole life had to be in machine language?
I would hate it.
I would hate it too. And as a matter of fact, when computers were first invented, the very first computers were very first invented, what do you think they invented first? The computer or the operating system?
The operating system.
Oh, no. No, the computer is hardware. Operating system is software.
Okay.
Are you with me?
Yeah.
So they had to build the hardware first. Are you with me?
Mm-hmm.
And so when they built that hardware, the very first, I'm talking about the pioneers back in the 50s, yeah, late 40s, early 50s. They actually had to program in machine language. And the way they would do it is there would be a row of switches on the front panel, and you know how a machine language instruction is like ones and zeros, and so up was 1 and down was 0, and they'd go up, down, up, down, and they'd put the data there, and physical switches, and then there'd be a row of switches for the address, and they'd put that address in there, and then they'd press a button, and that instruction would go to that address. And then they'd switch, and then da-da-da. How would you like to put every byte in the program like that?
That couldn't have been effective.
Well, I mean, that's all you could do. I mean, how else are you going to do it without an operating system? You know, the point is that they had to write their programs in machine language, and then they pressed a button, and the machine actually went through and did its thing, and then it stopped, and then they could see, and then they could query what the, yeah. So very soon after that, they knew that was extremely tedious, and so you know, they invented more and more tools to help them load their programs and execute them efficiently. And over the years, what happened was they developed, you know, an operating system. They developed an operating system is a program that helps you manage the other programs that you really want to execute to get your work done, right? Nobody, nobody wants to just write an operating system in and of itself. The purpose of the operating system is for us to be able to easily manage jobs that we actually want to do. The operating system is a means to an end. It's not the end itself. Are you with me? Okay, so here's one of the things that here's what happened like in the evolution of programming. What they decided was, so early on, what they decided was, you know what? I don't want to be able to have to memorize the ones and the zeros and stuff like that. So they invented a language called assembly language, okay? And so here is what we're going to learn, what they did historically. They invented assembly language, and what they noticed was that, after a while, in fact, you guys have probably gotten pretty good at this. After a while, what's the C1 instruction?
Load.
Oh, I thought that was the output. Wait, what's the output in?
5.1 is output.
Okay, so you know 5.1, right? You've done it enough to where you know 5.1 is the output instruction, right? Okay, so after you can imagine after you've done it a while, you could get really good at memorizing what the hex is and stuff. But that's kind of why should you have to memorize all that stuff? Wouldn't it be easier if you could write? Wouldn't it be easier if you could write a like a mnemonic? So instead of having the output instruction, why not, you could have an abbreviation for what that output instruction is. And then you could write your program using those abbreviations, and then you could give that program to a clerk. and the clerk could have a table that has what those, what those words are and what the machine language is, and then the clerk could just translate from that to that. And so those clerks were called assemblers.
And it was actually a person who did that?
And it was actually a person who did that. It was a person who did that.
So assembly language was just a shorthand.
It was a shorthand so that the engineers could write the programs and not have to worry about memorizing all the details of the binary.
Okay.
Are you with me? So literally that's what happened. So now here's what they did. Here's how assembly language works. First of all, we have to recognize the fact that there are two types of bit patterns. All right, some of those bit patterns represent instructions and some of those bit patterns represent data. Yeah? And you know how this works. You put the instructions first, then you put the stop instruction, and then you put your data after it. Okay, so what we need is a way to have a shorthand way of indicating what those bit patterns are, and we'll use a different scheme for doing instructions as we do for doing data. Are you with me on that? Okay, so first of all, for instructions, what we have is we have mnemonics. This is M-N-E-M. It's pronounced mnemonic. So the first M is silent. It's not mnemonics. It's mnemonics. And what is a mnemonic?
It's a name for something.
Yeah, it's more than just a name. It's kind of like a...
Like a short synonym?
It's a memory, yeah. I'm not sure what the etymology is, if memory is in there or not. But anyway, it's okay. So here's a memory device. Every good boy does fine. What's that mnemonic?
It's the treble clef.
Yeah, it's the notes on the what?
The bars of sheet.
On the lines. Yeah. What's on the spaces? Face. F-A-C-E. Those are the notes on the spaces. You guys who know music, right? So it's a memory. It's a memory device. So what we do is we identified which part was the opcode. Which part was the opcode? That was the first group of bits. The first group of bits that say what kind of instruction it is, right?
Right.
So what we're going to do, what they did is they said, okay, what we're going to do is we're going to have a mnemonic for each opcode, so that we don't have to memorize the bit pattern. We can just write down this mnemonic, and then what we'll do is we'll have letters for the addressing modes. Okay. And then so that's how we'll do the instructions. Now for the data does not have an opcode. Are you with me?
Right.
So instead of these being, so for the data we use what are called pseudo ops. So now what does pseudo mean?
Fake.
Fake. So yeah, so pseudo op means, well, these aren't really ops. These aren't really operations. They're pseudo operations. They're data. So that's the terminology that you use for the way you make abbreviations for the data bits that are supposed to be interpreted as data. Okay, they are also called dot commands because pseudo-ops begin with a dot. That's a common convention in assembly languages. All right, so let's take a look at how. So now that's the idea, and then what happened was the programmers would program in assembly language using mnemonics and letters for the addressing modes, and then they would use, or some other notation for the addressing modes, and then they would use these pseudo-ops for the data, and so they would write all their programs like that, and then they would turn it over to a clerk, at lower pay grade, so that you're not, because it doesn't take as much skill to do. It's a clerical activity. It doesn't take a whole lot of skill just to say, okay, I know when I do this, I have to look up the table here, and it's kind of repetitive, and you translate it to the binary, and then that binary can be loaded in the computer. Is everybody clear on that? Mm-hmm. Okay, so let's take a look first at the instructions. Now, first of all, let's take a look at the addressing modes. So, you recall that there is an addressing AAA field? Mm-hmm. And AAA, how many combinations of AA There's 8. And so, you already know the names. Okay, so here's a table that has not only the names, but the letters that we use in assembly language for denoting that addressing mode. So now instead of saying 000 in hex, what can we just use? I, lowercase I. And instead of having to memorize, 001 is direct, 001, we just put what? The letter D. And instead of 010, we use the letter N. Instead of 011, the letter S. Instead of 100, the letter SF. Letters SF. So do you, and do you see how these kind of are, these letters, they sound like what the addressing mode is, right? So I for immediate, D for direct. Unfortunately, indirect also starts with I, so we can't use I, so we use N for indirect. Are you with me? And then SXF is stack indexed deferred, and SF is stack relative deferred. So that's the table with the letters. So this table, you'll have this table on the exam. Okay, so you don't have to memorize this. But you do have to memorize the von Neumann execution cycle. Okay. Now, here is the table, and this is the table that's on the inside front cover of the book that has the mnemonics for every instruction in the instruction set of the PEP-8 computer. Are we good on this? Okay, so for each opcode there is a mnemonic. So the first instruction is called stop, and etc. and etc. BR and is the branch unconditional instruction that has opcode 0000, 010, and then what the addressing modes are that can be used for that. Now here is a really interesting part of the figure. This is the part that you're going to like. Do you remember? Okay, so here we have the rotate right instruction, right? The one after that is the NOP instruction, which stands for unary no operation, and that's a trap. Remember, that's a what we said, the trap and trap. And now, what do you see after the non-unary no operation trap? What instruction do you see?
Decimal input.
Yeah, the decimal input. So now, you guys, this instruction is not available to you at below the operating system level. But now that we are doing the assembly language level, what do we have below that's going to provide this service for us? We have the operating system. So now with this operating system in place, we have available to us a decimal input instruction and a decimal output instruction. Now how did we output a decimal value before?
We had to change it.
We had to change it to ASCII, and we only did it one character. Guess what that DECO, guess what that DECO instruction does?
Changes it to ASCII and
Not,
multiple characters?
yeah, not just 0 to 9. It will take a 16-bit quantity in, ones and zeros, and guess what it will do? It will check to see if the first bit is 1 or 0, and if it's 1, it will know that it's a negative number, and it will actually go through and analyze every bit in that thing, and it will convert it to the correct string of ASCII characters that represent that number, and output the string of ASCII characters, the whole string, not just the one digit. Are you with me? Now, can you imagine what it's going to take to do that?
A lot.
It's going to take a lot of programming to do that. And where is that programming?
Operating system.
Yes, and what part of the operating system? Remember the different parts of the operating system? There is actually two.
Trap handler.
Yes, that's in the trap handler. That is in the trap handler. So what happens is when the machine gets this 00110, that causes an automatic branch to the operating system. The operating system takes over, the trap handler takes over. It figures out what that instruction is, and it actually does all the processing to do that. Because, a machine, that kind of processing is never, the decimal output instruction would never be in the hardware of the machine. You see what I mean? But a trap instruction is. Trap instructions are common. I mean, this is a common mechanism. All right, so this trap instruction does a decimal out. So not only can we do decimal input, we can also do decimal output. We can also do what? Stro, which is what? String output. We can do, as well as our character input and character output. But see, the decimal input, the decimal output, and the string output, those are all trap instructions. So the operating system actually does those. And then, going on to the next slide here, here we have our usual load byte, etc. Now, let's take a look at this. Let's take a look at this add instruction. So you want to over here. So look, here's how you would write the add instruction in assembly language. What does it say over there on that figure? Add ADD, what's the mnemonic? ADD,
SP. Oh,
it's ADD in that little lowercase r. And that little lowercase r can either be what?
0.
A 0 or 1. So the way you do this in assembly language is you would write ADDA, or you would write ADDX.
Accumulator.
And so this is add accumulator, this is add index register. Are you with me? Okay. Does everybody see that? And then what you would do, okay, and then what you would do, so suppose you want to add to the accumulator. Well, now what comes, when you did the add instruction, what else did you have to give it after the add? What did you give?
Location in memory.
Yeah, the location in memory. Now, you can write the location in memory in hexadecimal using that 0x notation. So this could be something like this. Add a 0x something like 0057, if that's where you wanted to add it from. All right, you see what I mean? So there's the 0x for, it means this is a hex constant. Okay, and then how do you indicate the addressing mode? The way you indicate the addressing mode is you put a comma and then the letter. So direct addressing would be like this. So this would be add x from memory location 0057, direct addressing. And then you don't have to do, you see what I'm saying? You don't have to figure out all the, and now here's the other thing. Here's the other thing. After you do this, after you write your program using this notation, then what you do, now in the early days what they did is they took a program written in this notation, right? And they would give it to the clerks, right? And the clerks were the assemblers, and the assemblers would look up. Now, if I gave you this, could you convert this to hexadecimal machine language? I think you could be an assembler. Right? If you had a job as an assembler, you'd be qualified. You would be qualified. I know, but you'd be qualified to do it, because what would you do? You'd see ADD, you'd look that up. A would mean 0, so you'd put the 0 there. And then this is 0057, but then the D would go over in that AAA field. Now, does everybody see how to do that? You could
710057.
You already even can do it in your head. It's pretty repetitious, isn't it? Mm-hmm. I mean, because you could do it over and over again. After a while, you'd learn a few of the frequently occurring combinations, and you could get pretty good at it. You might even memorize everything and could do it. Mm-hmm. All right, now comes time for another big concept. What is the fundamental question of computer science? Did you?
Efficient.
No. Did you even know that computer science has a fundamental question? There is a fundamental question of computer science. In fact, it's so important, we're going to come over here and write it.
Efficiency.
The fundamental...
What can computers do that we can't?
Oh, that's very close. Yeah, in fact, that's basically it. The fundamental, check this out, you guys. The fundamental question of computer science is, are you ready for this? Quote, what can be automated? That's the fundamental question of computer science.
You want to automate everything.
Well, the question is, what can you automate? Because look, and what's the most powerful thing what's the most powerful statement in a programming language that makes the computer just be able to do stuff that helps us out so much?
Assignment?
Well, that, and what else? What can computers do that humans hate doing? Math, that's another thing, yeah. So add, subtract, multiply. So can people hate to do math? The computers can do the math for us. What else? Yes. The one thing that humans hate is, like you said, you could take that job, but you'd hate it.
Yeah.
Why? Because you'd be doing what?
The same thing.
The same thing over and over and over again. Over and over and over again. We hate repetition. The loop is an amazing, right? Because The machines, they'll do the same thing over and they won't get tired. They don't complain, they don't ask for a raise, they don't get carpal tunnel syndrome from writing the same thing over, I'm translating these things, my arm is, get me benefits, you know. No, they don't want benefits, just plug them in, get some power, plug them in, program that loop, and it will do the same thing over and over and over again. So, and furthermore, I mean, all of the advances, all of the stuff that makes all of our world just seem so great because of what computers do, what is the computer doing? It's automating repetitive tasks. Whether it's a robot, you know, like a robot-controlled vacuum cleaner, or, you know, R2-D2, or, you know, whatever it is, it's what can be automated. What can we do to help us, you know, do stuff that would be repetitious? Well, what's one of the things that they discovered real early could be automated?
Math.
Well, no. What?
The assembler job.
Yeah, the assembler job. So really early on, what did they do? They wrote a program that would take an assembly language program as input and output the what?
The machine.
The machine code. The machine code. And when they did that, guess what happened? All those assemblers lost their jobs. Now I ask you,
They're good.
was it good or was it bad that in the long run, that those assemblers lost their jobs?
Great.
Good.
It was good in the long run. Although it caused pain in the short term, it was necessary. In fact, not only was it good, it was necessary in the long run. Because can you imagine where we would be if there were no assembler programs and we still had to hire rooms and rooms of clerks to do that translation? It's not viable. And not only that, the society would be less wealthy. We would be poorer as a result, because they would be doing stuff that could be done by a machine. So the lesson is, anytime you hear a politician say that technology is losing jobs and blah, 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 you think twice about that. That's my little political commentary, economic political commentary for the day, is that computers by nature put certain classes of people out of work, and it's hardship for them, but it's necessary. You hate to be hard-nosed about it, but I mean, can you imagine what would happen if we didn't have automatic looms? You know, the Luddites. What if the Luddites had won, and we had to weave by hand? We would be more poor. The poorer people would be even more poor, and the middle class wouldn't exist. See? So you've got to be realistic about it. And here's one example. Right? And furthermore, do you remember that in the very first day, one of the things we said we were going to do in this course?
Write a big fat program.
Write a big fat program. Guess what that big fat program is?
In assembly language?
No. Guess what it will do?
Translate.
It's going to be an assembler. You are going to write an assembler that translates from assembly language to machine language. So you will actually write one of those things and put some people out of work. You see what I'm saying? You see what the idea is? Okay. Now there is an assembler is built into the PEP 8 app. So we can write our programs in assembly language from now on. Right? And so, but I think it's important that you know how to write in machine language, even though you will probably never ever, how many machine language programs have you written now? So maybe two, maybe you'll write another, I don't know if you'll write another one or not. Probably not. Oh, by the way, here's the homeworks, yeah.
So we're going to use Java to write.
So here's what you're going to do. That's interesting, isn't it? What you're going to do is you're going to use Java, so that's one programming language, higher language, to translate what? A program in this language, so that's the second language, into what? Into machine code. So there's going to be 3 languages. One language for the, right? Are you with me? That's what's coming up. All right? So, here we have on our next slide, these are the unimplemented opcodes. We have a no-op. NOP is called a no operation. So we have a couple of no-op instructions. And then we have DECI for decimal input trap, DECO for decimal output trap, and STRO for string output trap. And I'll show you, we'll give you examples of some programs that use those instructions in a minute. And then And now what did we say? So it's everybody sees how to write an instruction, you know? Now, the other, and what were the other kinds of bits? These are program bits, and what are the other kind of bits that we have to be able to get into our program? Data. And what were those called? What was it called? The
Pseudo-ops.
Pseudo-ops. Okay, so here are the pseudo-ops. The PEP8 assembly language, all assembly languages have pseudo-ops. They're also called dot commands because they begin with a period. That's how the assembler knows that it's a dot command. It checks for the period. If there's a period there, a dot, then, oh, this is a pseudo-op. All right? It translates the pseudo-op. By the way, as we go through this now that you know you're going to be writing an assembler, you think about how you're going to automate this in your program. Yeah? Are you with me? Okay, so let's take a look at these pseudo-ops. First of all, there's a .addrss pseudo-op. That's the address of a symbol. There's a dot, I don't think we're going to, well, yeah, we will. We're going to, and then there's a .ASCII, which is, if you want to write down a string of ASCII bytes, the assembler will convert it to the hex, to the machine language. There's a .block command, a .burn command. The .burn command initiates a ROM burn. You won't ever need to do that. It's only used once to burn the operating system in. Okay, and that's already been done for you. There's a .byte command, which if you want to specify a byte value, there's a .end. Now the .end in assembly language corresponds to the ZZ. Are you with me? And then the .equate equates a symbol to a constant value, and then a .word is a word value. And how many bytes is a word? 2 bytes.
In your language, in PEP8.
Right. Right. Okay, and now comes, are you ready for this? Now comes our very first assembly language program. Now check it out, sports fans. First of all, what do you notice? This is in figure 5.3. First of all, now, how do you put a comment in assembly language?
Semicolon.
You start it with a semicolon.
Can start naming our.
Now, and as a matter of fact, not only can you, you must, otherwise you'll get -1 for not putting your name and the date and the assignment number. So now you can do it. Okay, now it's not optional anymore, okay, because we're in assembly language. So there's the name, date, assignment number. And now, this is that program that outputs the characters hi, H-I. Are you with me? And see how it does it? So what you write down is you do charo, character output, and then 0x0007, comma D. All right?
Question? For comments in assembly language, you have to go to the next line for the comment to end.
Yeah, it's like //. Yeah, it's from there to the end of the line. Yeah, that's what the comment is. And you can put the comments also. Yeah, you see, there's that where it says output H. It's like that's a comment. Are you with? So it's like // in C++. Are you with me? So what is that? The first says character output from 0007 using direct addressing. Character output from 0008 using direct addressing, that outputs the I, and then stop, and then the .ASCII hi. And then what the assembler does is it translates from that assembly language to the machine language. So you see here is the assembler output. And then you would have to load that and you run it. When you run it, the output comes out HI.
So .ASCII, when you give it HI, fills in 2 bytes?
Whatever is in between the quotes, each character.
Each character it takes.
You could, and notice that, and so the assembler has the ASCII chart is, built into the assembler.
So the H is at 07 and the I is at 08?
Yes.
Okay.
And how do we know that? Because the character output is what address is the first charo? That's 0. So it's 012. The next charo is at bytes 345. Stop is at 6. So the H is at 7. Now do you see how to count that?
So .ASCII isn't.
Okay, the ASCII is a dot command, and what you do is you write dot.
Take memory.
Yeah, that's where the 48 and the 69 are.
Well, but the 48 is the H, right?
Yeah, the 48 is the H.
But the .ASCII itself doesn't take up memory.
No. The .ASCII tells the assembler Now this is a good question. The .ASCII tells the assembler that what's coming next is a string of ASCII characters, so look up what that is in binary and create
Yeah,
that
it
and
wouldn't
create
be
that.
different, because you wouldn't put anything in there.
It
in
puts the
machine code,
right.
Put the values in.
Yeah, yeah. Do you see that the stop generates that 00 byte?
Yes, after that.
And then that .ASCII generates the 48 for the H and the
It
69
takes the H and converts it to 48
and puts it there.
And then-
Yes. And guess what? Your program's going to do that.
So if we had three things, there'd be three caros instead, and then they'd
Yeah. Well, and then ASCII, you could put a string of ASCII characters there.
Okay.
All right, now, somebody memorize this program.
I wrote it
I wrote
down.
it down.
Okay, are you ready for this? Let's do this. Let's show you. Oh, wait, one more thing, one more concept. Actually, let me just go through one before we do the demo. Okay, so you see then that what the assembler does in figure 5.4, you see how this arrow, it translates from level what?
5 to 3.
From 5 to 3. Does everybody see that that's what it does? Okay. And furthermore, now what three things does a program do? Oh, I shouldn't have given you the slide first. It does input, processing, and output. So for the assembler, what's the input?
The assembly language.
It's the assembly language program. The processing is the assembler. Are you with me?
Yeah.
And the output is 510007004869ZZ. Yeah? Is that cool? So now here's how it works. Okay. So, little demo time. Okay, so here is our demo. So here's the PEP8 app. And now, instead of writing your machine language and putting it here in the object code pane, you put it up here in the source code pane. So watch this. First we put name. So this is, see how that works? Just type it in.
Green when it's commented.
Yeah. Example, whatever. And now, what did you say we did? How did you say we did that? What was Caro?
Caro.
Now watch this. CHARO.
Hey, keyword.
Keyword. And check this out. RO.
Doesn't matter.
Doesn't matter. Okay. But you'll see what's really cool about it. So character output from what?
0x0007.
0x0007. Direct.
Can you put a space between
Caro.
them?
Okay. Okay. You want to put a space?
Like after-
0x. What was the next one?
Zeros.
Wait.
0008, space, comma, space, what was it, direct? Okay, you want to put some space, and then what was the next one? Stop, okay. And now, yeah, notice this,
Enter, double enter.
Dot
ASCII, and then, what do we have?
Equals.
HI, right? You with me? See how it's recognized and color-coded? And then dot end is necessary for the ZZ. Now watch what happens here. Under build, we can do assemble. Now watch what happens when we do assemble. Boom. Now, not only does it give you this object code, 510007, 510008, 004869ZZ, it also, down here, gives you a nice formatted, isn't this nice? A nice formatted, with everything all changed to uppercase, .ASCII, All right? So guess what, you guys? From now on, what you turn in is this, and I don't care if it's uppercase, lowercase, I don't care how sloppy it is, because the assembler will clean it all up for you just like this.
How nice.
Isn't that nice?
Oh, and it gives the address.
And not only that, what does it give you here in this column?
That's the object code.
That's the object code. It gives you, so it had, right here you can see character output 0x00Z, 510007, 510008, 00, and it gives you the address. Is that slick or is that slick?
Should we write that?
You write that.
Oh.
We're gonna be able to do that.
Well, actually, I'm not sure. Actually, I don't remember. I think in the project I don't.
All the formatting.
Oh, wait. Maybe do you do the listing? I don't remember. I don't remember if you have to do the. I think you do. No. I think you do. I think you do. But I'm not sure.
It might just be the object.
Yeah, it might just. I don't remember now. Okay, but is everybody clear? And at this point, what can you do? at this point, you have this in the object code pane, right? So what can you do? You can do load. Now watch what happens when you load. Boom, over here it's loaded.
And that will only work once it's in the object code, right?
Yes, only when it's in the object code, all right? And then you can do,
Run object or run source. Which one?
yeah, well, okay, yeah, good question. Watch, well, okay, here we can run object and boom, high comes out, right? Now, of course, if you wanted to, before you did this, you could just do what?
Run source.
Run source.
And it'll run assembly.
And it will load, it will
Also assemble.
do this and do. But of course, everything, the ultimate shortcut is what? Assemble, load, execute. And guess which icon that is?
Green.
That's this one.
Oh.
So really is all you have to do. But now what if you make a mistake, you guys? Here's what happens if you make an error. Suppose you misspell this. C-H crow, okay? And now if you try to run it, if you try to run the source, look what happens.
Oh, yeah.
Error, invalid mnemonic.
Hey,
All right?
invalid address? Give it-
Invalid mnemonic. Okay, so you say, now if you want to, what you could do is you could come here and do,
Start debugging the source.
no, you can't debug it until it gets
Oh, okay.
compiled.
Ah,
You could, wait, where's my edit? You could remove error messages
Oh, okay.
if you want to, and then correct it. But if you don't have to if you don't want to. You could just correct it like here. So CHARO. And then because whenever you run it, it removes the error messages if they're there. So you can just do it, boom, and here, it worked. Are you with me? And of course, if you want, what is this little ladybug there? Start debugging source. So watch this. You press this, and it puts you, and now look what happens over here. It puts you in a listing trace, okay? And as you single step through, watch what happens on this left panel on the left. Boom, H, boom, I, boom, stop. So you can actually go through and trace one step at a time. Is that slick or is that slick? And here, of course, it shows you the CPU. And normally you can be in this mode because after a while you don't have to see the memory in hex. Yeah, but you always can if you want to. All right, and so here we start debugging. We start debugging, and we single step through, and we can see what instruction is being executed and what the registers in the CPU are, and then the I, and then we're going to execute the stop, and then the stop executes.
What? If you did like ASCII HA.
Yeah, and by the way, these are tabbed here, right? So we come back here to this. Is everybody clear on that?
ASCII loads the characters into the memory.
No, hold it. This ASCII produces this.
So it loads
That's-
it for you.
The loader loads. The .ASCII translates. The assembler. Now this is important. Actually, this is a really important question. The assembler translates.
Right.
Are you with me? The assembler is a program that translates. Here. The assembler takes this .ASCII, and when you do assemble, like over here, when you do this assemble option, then what that does is that .ASCII creates this 4869.
So
Then when you load, then that goes into memory. Then this goes into, see, like here, when you do load like this, then whatever is here, this object code, that actually gets loaded into memory. Okay, so there's two different times that are important. One is translation time, assembly time. The other one is runtime. Actually, there's three times. There's translation time, load time, and then runtime. But
So if you put in ASCII like hello,
yeah, here, let's do it.
would it only just output
What?
HE?
Let's try it. Let's try it. Let's
Yeah.
try it. HELLO. Okay, so watch this. Here, so when we do build assemble, watch what happens. Oh, sure enough, it puts in HELLO. But what does this do? But what is,
But it's only gonna outprint the first.
it's only going to output HE.
Okay, good. I was wondering. Okay, so ASCII
So
just
there-
puts it in memory.
Yeah, it translates it to the sequence of bytes, right?
Perfect.
And now you guys, what you can do is, if you're not sure where those letters are going to be, you can write this program with just zeros here. You see what I mean? You can just write your program with zeros here if you don't know what the address is going to be. And then when you assemble it, then you can say, oh, that's down at 000700. You see, you can actually go and look, and you see what I mean. So and now look at how it did the hello. It's the 48658 so that's at addresses 7, 8, and 9, and then this is at A, and then this is at B.
So then promise you're gonna have to add more carols to output it. So then you can go-
Well, yeah, but what I'm saying is, if you wanted to do that, you could put more carols there,
And then it'll
and
show
th-
you
and it
the
will.
data.
You could do an assemble once and see where it is. And yeah, is that cool?
That's cool.
Do you like it?
Yeah.
Did I? All right.
I'm not gonna like make it.
No, well, yeah, you're gonna have to write your own. Yeah, later on, you're gonna have to write the assembly. Okay, so that concludes the demo. Okay, so that's the demo. Now, here's another program in assembly language. Now, what does this program look familiar? No, you remember you put UP and it outputs what?
PU.
PU. Okay, remember how that worked? Remember with that program? Okay, so here's a program written in assembly language. All right. So now let's take a look and see what new features are. By the way, I don't bother to put the
Input.
I don't bother to put the
Name.
the documentation just to save space on them. But you have to. Okay, so don't. All right. So first one is what? Character input. So character input to what location? D, using direct addressing. Character input from E using direct out, and then character output from E, and then character output to D. And then stop. And now we have a new pseudo-op. Dot block.
Okay.
Now what does it look like dot block does?
0, 0.
It what that does is that reserves storage. Now, so what comes after the dot block?
How much space you want?
How many bytes?
Oh, okay.
Are you with me? So if you want to reserve 2 bytes, it would be dot block 2.
Okay. And you would have to do that for any numbers or anything, right?
Yeah, what's going to happen is C++ memory model. What's the first part of the C++ memory model?
Global variables stored.
Where are they stored?
Fixed location.
In a fixed location memory. How do you suppose you're going to set up a fixed location in memory?
Dot block.
With dot block. So if it's an integer variable and it takes 2 bytes, you'll say what? Dot block 2.
Why didn't you just do dot block 2 for this one?
Well, I could have, but because. Yeah,
Oh,
we could have done dot block 2, but I wanted to be able to document
For the
that one was for the first character and the other one was for the second character. So you're right, we could have substituted those 2 dot blocks with a single dot block with 2, and it would have done the same thing. Are you with me? Is everybody clear on how that works? And I won't bother to demo this.
Well, when we input a character, I know we've already demoed this, but are we inputting it like in ASCII, like in a translated for us? Like if you put in
It's character input, so there's no translate. So it's that character. And remember, there was an input pane and an output pane.
But it stores that character as an ASCII value, right?
Yeah,
Okay.
yeah, it comes in as right. So there's actually there's also there is a interactive mode. So if you're in interactive mode, you can actually type UP, and as you type the U, that ASCII character goes, and the P, ASCII character goes. But that's what happens on all these keyboards. Okay, in the keyboard, when you're typing those, that information is going in ASCII. All right, is everybody clear on how that one works? That's figure 5.6. Okay, here's another one. What is this one doing? What is this program doing?
Load to the accumulator?
What is it? What is?
Or store by.
adding.
Does this look familiar?
Yeah, it's just adding.
Yeah.
Did we not do this? Didn't we do this program before?
Adding and outputting.
It's adding what's it adding? The what?
3.
The 5 and the 3. Is everybody clear? It's adding the 5. Okay, so now let's see. How does it add the 5 and the 3? Now watch this. How did we have to add the 5 and the 3 before? We had to load it, and then we had to add it, and then what did we have to do?
Convert it.
We had to convert it to ASCII. But look, you're going to like this. Well, now what do? We load accumulator from what location?
11B.
Yes, no, 0011,
Right.
using what addressing mode? Direct addressing, okay. And what's that 0011? Well, if you count it out, it's going to be the 5, right? And then what? Add.
What's that, 13?
What's that 13? That's going to be where the 3 is, okay. And then, oh wait, why am I converting the sum to a character? Oh, just so that it will be the exact same thing. Yeah. I thought, yeah.
So it's a mirror of our
Yeah, so it's a mirror of the old program. Okay, so because this shows you how the OR accumulator thing works. Okay, and then the store byte, the STBYTEA is the mnemonic for the store byte instruction. Are you with me? And that stores it at 0010, and then character output from that location. But now look, we have some new pseudo ops. So what's the first one is a dot block 1, 1 byte. Are you with me? Then a dot word. Now, what is dot word? This is not dot block, this is dot word.
A word value 2 bytes.
Yeah, so what it does is it takes that 5 and it
makes a 2 byte.
It makes a 2 byte 5 out of it.
And that's in hex, right? Not.
Well, the 5 here is decimal. If you put like 53, it would actually take 53 in decimal and convert it to hex for you.
This takes a decimal.
Yeah, if you want it to take a hex, you can put 0x
Dot word
5.
0x.
Like right there.
No, you could say dot word here. If you want it to be a hex word, if you want it to be hex, you could say dot word. You could say dot word, and you could say 0x57A3.
And what would it actually do?
It would take this 57A3 in hex and put it in that
And it would
word.
just be 2 bytes, and that would be.
It would be 2 bytes, and that would be it. Or you could say like this. You could say dot word. You could say dot word, and you could say, like 97. And this 97 would be converted to hex. This is a decimal. It would convert it to hex and do the right machine language. Are you with me?
Jam a day?
Okay, and now, and what else? So there's the dot word, and then the mask. Oh, actually, look, there it is. There's an example of dot word with a hex. Remember how we wanted to have the hex constant, the hex mask to do? So that's how you do the hex mask. Okay, but then the program executes. Look, do you see that the assembler output? That's what we had to write in hand before. But now we can write it this way, and the assembler translates it that way.
Andy.
Is that cool?
Yes.
Thank you. That's a long pause there. And there will be an even longer pause between now and when I see you on Thursday. So see you next time.
Bye.